Hello students, what I've got for you today is just a quick demonstration of how we would measure the resistance of a component. Now this component could be a light bulb, it could be a fixed resistor, or it could be a diode. Now what I've drawn on the table here is just a little circuit diagram showing the components you would need to do this. Now the important thing about this is it does come up quite a lot in questions on the exam papers, asking you to describe experimentally how you would measure the resistance of a component or investigate what happens to the current through a component when you change the potential difference across a component. So here we go. This is the circuit diagram. Over here we have a cell, which is the power supply. Now in the lab we quite often use DC power supplies plugged into the mains rather than use cells, just to save us on running out of cells, but it's exactly the same idea. You have a variable resistor. I'll explain why you need a variable resistor in a minute. Here is your component. Now I've drawn on this circuit diagram a light bulb, but as I said, it could be a resistor or it could be a diode replacing that. Across the components, and the important thing is that it is across the component, not in series with it, it's in parallel with the component, is a voltmeter. And the voltmeter is measuring the potential difference from one side of the component to the other. In series with the component, we have an ammeter. And the ammeter, of course, measures the current going through the component. Now, if you set up the circuit like this and switch it on, you'll get a value for the potential difference, you'll get a value for the current, and there's a simple formula, which you should have learned, which will allow us to work out what the resistance of the component is. Basically, the resistance is defined as the ratio of potential difference to current. So it's potential difference, symbol V, divided by current, which is symbol I. So that's what the circuit would look like on a diagram. And I'm just going to show you now how the circuit would be set up in real life, because of course in real life everything doesn't look like it's got nice straight lines like on a diagram. So I'm just going to adjust the camera slightly so that you can see the equipment that we've got in the lab in order to do this experiment. So I've got a power pack here. As I said, we'll use a power pack rather than a cell, but it does exactly the same job. What I'm going to do first of all is just make a loop, a simple series circuit of the power pack, the ammeter, the component, which in this case is the light bulb, and the variable resistor. So obviously you'll need some wires to do this. So I'm just plugging it all in one loop. So I'm going to turn it on and just check that the circuit is working, that I measure a current and that the light bulb comes on. This being physics, it doesn't always work first time. We sometimes have practical problems such as loose wires, bad connections, and that's just one of the things when you're doing experimental physics. You just have to check and see and take steps to fix if necessary. So switching it on. Now it does take a couple of seconds for the power pack to warm up, this particular design of power pack. So it's warmed up now, it's on 12 volts, so I've set it to 12 volts output. Light bulb is not coming on, but of course that could be because the variable resistor is turned too high. So I'm just going to change the variable resistor. And there we go. So you can see that the light bulb has indeed come on. Now the one component I haven't plugged in yet, I've saved till last, is the voltmeter. I wanted to plug this in last because I just wanted to remind you that you have to be very careful when you plug in the voltmeter. A lot of students by mistake will plug the voltmeter in series in the circuit. And if you plug the voltmeter in series, the voltmeter is a very high resistance, nothing passes through the circuit, and you're not going to be measuring the voltage or the potential difference across the light bulb. So the important thing about the voltmeter is that you plug it across the light bulb and not in series with it. So you plug it in parallel. So I'm just going to do that now. So there we go. I've got a negative reading on the voltmeter. Now I can cure that just by swapping the leads around. There we go. I've got a positive value now on the voltmeter. So it's reading 9.1 volts. The ammeter, strangely, is not reading anything, which probably indicates a loose wire connecting there. So I've just adjusted that. The ammeter is now reading 1.4 amps. So there we've got two measurements. We've got the voltage across the light bulb. We've got the current going through the light bulb, 9.15 volts, 1.4 amps. We could, if we wanted to, just divide the voltage by the current and we would get the resistance of the light bulb in a certain number of ohms. Now, the interesting thing about a light bulb that you might be asked to investigate, or you might be asked on an exam to describe this experiment, is that the resistance of a light bulb is not actually a constant. And the reason for this is because if we turn the voltage up to a higher value, you'll end up with more current going through the light bulb. The very thin tungsten filament in the light bulb will get extremely hot. That's why it's glowing, and it'll glow even more. And it becomes very difficult for the electrons in the circuit to pass through the filament. So the resistance gets higher. So we might want to do an experiment with a light bulb where we're investigating how the resistance changes with voltage, or indeed how the current changes with voltage. And that's where this variable resistor comes in, because the variable resistor will allow us to change the voltage just across the light bulb. Now, we set up the power pack to output a constant 12 volts across the whole circuit. But by varying the resistance of the variable resistor, we can change how much voltage we get across the light bulb. So, for example, if I increase... Now, unfortunately, this variable resistor is a little bit jumpy. It's not working quite as well as I'd hoped. But if I increase the resistance of the variable resistor, I will increase the potential difference across here and therefore decrease the potential difference across the light bulb. Now, it will always add up to 12 volts. So at the moment, I've got 8.7 volts-ish across the light bulb, which means that the remaining 3.3 volts is across the variable resistor. But I can actually change that by varying the variable resistor. Now, for some reason, that's actually gone off. Okay, don't know why. Okay, as I was saying, this is playing up a little bit, this variable resistor. Now, in fact, we don't have to use the variable resistor in the case of these power packs. What we could do is just bypass the variable resistor and just use the power pack to do exactly the same thing. In fact, the power pack is a lot smoother than the variable resistor. So I'm changing directly on the power pack how much voltage I'm going across the light bulb. That is a rather easier way to do it with the setup we've got here. The only thing is you will need to learn about variable resistors, because you might not have a power pack, you might just have a cell, which you can't change the output of a cell. So you might need the variable resistor to change the voltage across the light bulb. Okay, so that's the actual experiment. What about the results of the experiment? Now that's the important thing, because there are 3 different components that you might be asked to test with an experiment like this. You might be asked to test a light bulb, you might be asked to test a fixed resistor, and you might be asked to test a diode. Now let me explain what the different results are that you would get. Now, first of all, the light bulb. As I said before, the resistance of the light bulb is not constant. So I'm just going to show you, by drawing on the table, a graph that explains how, as you increase the voltage or the potential difference across a light bulb, the current will vary. So I've drawn a graph with voltage on the x-axis. Now, This represents what would happen if we measured several different voltages across the bulb, and then you'd get several different currents. So on the y-axis, I'm going to give you the current. Now, typically for a light bulb, we end up with a relationship between voltage and current that looks like this. As we increase the voltage, the current will also increase. No big surprise there. Okay, the more push we give the electrons, the more electrons we have going through the light bulb every second. However, the increase is not constant. So initially, the current would go up in very big jumps as the voltage increases, but then as the voltage gets higher and higher, although the current carries on increasing, it goes up by a smaller and smaller gap each time. And that is because the resistance is going up. If I draw a curve there, you end up with a curve that looks a bit like this. So this is the voltage current graph for a bulb. Now, if I take any point along this line, so for instance, if I take this point here along this line, I could read off the voltage at that point there. I could read off the current at this point here, and I could measure the ratio voltage divided by current. That would give me the resistance. I think what you can probably see is that the ratio of voltage divided by current at this point here, because the current is fairly small compared to the voltage, okay, there's the current, there's the voltage, you would get a high resistance at this point here. So when the voltage is very high across the light bulb, you get a very high resistance. On the other hand, if I turn the voltage down to this level here, and then I measure on the line what the voltage is here, and I measure across what the current is here, you see we've got a different ratio here. We have a small voltage, but relatively a large current. So small voltage, large current. So if we did the ratio voltage divided by current here, we'd see that we had quite a low resistance, at least relative to what we've got up here. So down here you have a low resistance, up here you have a high resistance, and that's, as I explained, it's because it's very difficult to push the electrons through a light bulb when the light bulb is very hot. The tungsten atoms in the filament start oscillating with a very large amplitude, and it becomes very difficult for the electrons to pass through the filament. Another way of saying that is that a light bulb doesn't obey Ohm's law. Ohm's law says that the current should always be a constant in a metal conductor if it stays at a constant temperature. Of course, with the light bulb, it hasn't stayed at a constant temperature. It's heated up dramatically, so it doesn't obey Ohm's law. It's a non-ohmic conductor. On the other hand, if we did the same thing for a resistor, that's a fixed resistor, what you end up with is a graph that doesn't look anywhere near as interesting as this. What you would end up with is a graph that looks like this. So exactly the same experiment. So I'm going to change the voltage and I'm going to measure the current. So we've got voltage against current. So this is now a fixed resistor rather than a light bulb. For a fixed resistor, as the name suggests, the resistance always stays constant. It doesn't change. That means the ratio of voltage to current always stays constant. So if you take different measurements of the voltage and read off different measurements of the current, the two are directly proportional to each other. Now, we all know what a directly proportional relationship looks like on a graph. It's a straight line that passes through the origin. So you would get something like this. There's the origin. As you increase the voltage, the current increases in proportion. So you get a nice straight line. And I don't have a ruler on me, but if I did, I'd be able to put my ruler on this graph. and draw a straight line going through the graph. And it doesn't matter any voltage you take, you could read off the voltage and the current. So I could read off the voltage at this point here and read off the current. And I could do voltage divided by current at any point on that line, and it would give me the same value, because remember, R, the resistance, equals V divided by I. And in this case, it's a constant. It doesn't change. So this is the graph you would expect. That was a bulb previously. This is the graph you would expect for a resistor. There is a third component that you could do exactly the same experiment with, and this is a special type of component called a diode. Now, a diode belongs to a family of components which are called semiconductors. The symbol for a diode looks a bit like a, I'll just move the camera there. It looks a bit like a sort of a play stop button on an old video recorder. Basically, the symbol indicates in a very simple way how current behaves with a diode. Diodes only allow current to go through in one direction. Unlike a resistor and a light bulb, which doesn't care which direction the current flows, if you plug in a diode the wrong way, it's called the reverse bias, the resistance of the diode would be huge and no current would flow through it. That's equivalent to trying to push current through in that direction. However, if you plug in a diode the correct way, the forward bias direction, the current can easily pass through. The resistance drops. So that would be the current going through that way. So it would depend for this diode which way round the cell is pushing the current. So if I put the cell that way round, that's positive, that's negative, the current would flow that way and everything would be good. The diode would be switched on. Now I could do an experiment just like with the bulb and the resistor to look in detail what happens if I change the voltage slightly, what happens to the current that passes through the diode. And the diode would look like this on a voltage current diagram. So I'm going to do the same thing I did before. I'm going to plot voltage on the x-axis. Now this time, because it matters which direction the diode is plugged into the circuit, I'm going to put 0 volts in the middle, and on one side I'm going to put positive voltages, which means that the diode is forward biased, it's put in the circuit in the right direction. I'm going to go up to 0.6 volts on this side, so that's plus 0.6. The significance of 0.6 volts I'll explain in a minute. On the other side, well, we can put minus 0.6 volts on the other side. And we're going to measure current that's passing through the diode. Now, if the diode is connected the wrong way around, we get practically no current at all coming out. So if I measured a load of points here, they would all be pretty much on the x-axis because the current would be 0. So this is what happens if the diode is connected the wrong way around. However, if the diode is connected the right way around, this is what happens. Now initially, it's very similar in that you don't get hardly any current through. So if the voltage is very low, even if it's forward biased, even if it's connected the right way around, the resistance is still very high. You get hardly any current coming out. So these points here you can see are pretty much clustered on the x-axis. Very little current. But as soon as you reach a certain voltage across the diode, all of a sudden everything changes and the resistance of the diode drops and you suddenly get a huge current. Now for the most common type of diode, which is sometimes called a PN diode, the switching voltage, as it's called, is at about 0.6 volts. So that's why I drew this 0.6 volts here. at this point, the diode, if you like, switches on. Its resistance drops. It suddenly lets lots and lots of current through. So on a voltage current graph, this is what you would expect for a diode. As far as what diodes are used for, they do have a number of different purposes that they are used for. One use is to protect other components that are sensitive to current going through them in the wrong direction. So for instance, if somebody by mistake put the battery in a device with the negative and positive terminals the wrong way around, you wouldn't want to damage the device. So a diode could be in the circuit within the device to protect other components from current passing the wrong way through another component. Another use of a diode is to change alternating current into direct current. Alternating current that goes backwards and forwards. Direct current that only flows in one direction. And a diode, or more likely a combination of diodes, can change an alternating current into a direct current. And a third use of a diode would be to use this very sharp switching function of a diode. You can see that a diode suddenly switches on when the voltage across it gets to 0.6 volts. Now, sometimes you want another component to switch on very suddenly at a particular point and not change very gradually. So, for instance, you might want a warning light to come on very suddenly, depending on, for instance, temperature or whatever it is that's setting the warning light off. Now, if a diode is part of that circuit, it can produce a very sharp switch. So it's this switching characteristic of a diode is sometimes used in a circuit as well. There are other uses of diodes as well, but they're the main uses of diodes. So to summarize, you need to learn all three of these voltage current graphs and also the experiment that I used to get these voltage current graphs. So you've got the diode there, which is asymmetrical on both sides because it lets current through on this side, very low resistance at this point and a very high resistance if it's connected the wrong way around. You also need to learn what happens with a fixed resistor if you change the voltage. Well, you get a current that's directly proportional to the voltage, so a nice straight line graph. And then finally, for a light bulb, you get a resistance that increases as the voltage increases, as the light bulb gets hot. So you get this curved graph. And just as a last reminder, if I turn the camera around here, that is the circuit that you need to learn. So at some point in your books, you need to draw this circuit and annotate it as being the standard circuit that you would use in order to measure the resistance of a component or investigate how the current through a component varies with voltage. And the equipment that you would use is like this. Okay, so just to remind you again, you have a power pack, you have an ammeter to measure the current, you have your components, you have your voltmeter, which is connected across your components, so across the light bulb in this case. You have your variable resistor, which I actually took out because it was a bit jumpy, but if I put it back in again, let's see if it's working now. Oh, there we go. So our variable resistor is actually working. Okay, so we've got our variable resistor, and of course you need to connect it all together with wires. Everything is in series apart from the voltmeter, which is in parallel with the light bulb. Okay, I hope you understood everything there. If you do have any questions, either email myself or your subject tutor. And I hope that's all right for everybody. Thank you for listening.
So locking up there, sir.